Hello, thank you very much for watching. Welcome to this video series as support to the Automatic Control with Interactive Tools book. All the interactive tools described in these videos are available for free at the book website. Our goal is to introduce you in a fascinating journey to learn automatic control concepts using interactivity. Let's start. Interactivity is an amazing feature for enhancing learning. It allows us to immediately see the effects of changes. Effects that simply cannot be shown with static images. This makes interactivity a very powerful educational resource. It supports a learning by discovering approach, where students learn by actively interacting with the tools. By manipulating different elements, they can directly connect what they see with the theoretical concepts behind it. This is the main advantage of the interactive tools provided with our book. An advantage that cannot be fully described or truly experienced through written text alone. For this reason, the objective of this video series is to briefly show you these interactive capabilities and how they can enhance the learning experience. In this first video, we would like to introduce the different types of interactive objects as well as the graphic and text elements that you will find in the interactive tools. We will also explain how these elements are arranged on the screen. Most of the interactive tools have been designed following a consistent layout. In particular, many of them follow a quadrant-based pattern for the distribution of elements. Most of the visual elements appearing in the tools are interactive objects. Interactive objects can be easily identified. When the mouse pointer is placed over them, the pointer symbol changes from an arrow to a hand. Interactive elements are mainly available in the parameters section. Here, parameter values can be modified interactively using sliders. Specific values can also be set using text edit fields, or by selecting different options through radio buttons, checkboxes, or classical buttons. Moreover, all the graphs available in the tool contain multiple interactive elements. For instance, in the pole zero map, poles and zeros can be modified interactively by simply dragging them along the S-plane. Classical representations are used. Poles are drawn as crosses, and zeros as circles. Integrators and differentiators are represented by bold poles and bold zeros, respectively. Across the different tools, additional symbols and color patterns are used to represent other concepts. In plots showing time or frequency responses, interactive circles and lines are also available. These allow the user to modify different parameters directly on the plot. This is a very powerful feature. It allows the effect of a given parameter to be immediately understood by dragging directly on the time or frequency response. Graph scales can also be adjusted interactively. A gear wheel icon is located at the top right corner of each graph. By clicking on it, a new window appears, allowing the user to configure the graph scale. The user can select a locked scale, where the axes limits can be adjusted manually. Alternatively, a variable scale option can be selected, where the scale is updated automatically. Finally, all tools include menu options to save and restore sessions, reset the tool to its initial configuration, and access a tool-specific drop-down menu offering additional options. Coming back to the layout of the tools, for tools related to physical systems, the layout pattern is the following. The top left area is dedicated to interactive parameters and equations. From this area, the main parameters of the process for open loop and closed loop versions can be adjusted interactively using sliders and text boxes. The top right area shows the open loop or closed loop time response of the system. Comparisons between linear and nonlinear models are shown, and the operating point can be interactively modified. The bottom left region is used for the process representation. From this area, process parameters and operating point values can be changed by interactively adjusting the physical representation of the process. This option allows relating the process scheme with the process equations. And finally, the bottom right area displays the input signals applied to the system. For the open loop version, a step-like input signal can be interactively adjusted. This layout is common to all 9 tools related to physical systems, such as tanks, DC motors, the inverted pendulum, and the ball and beam process. For tools related to time domain analysis and design, interactive parameters are also available in the top left area. In this case, the bottom left region displays an interactive pole zero diagram. Here, poles, zeros, integrators, and derivators can be modified interactively. To add or remove poles and zeros, they can be dragged into or out of the pole zero diagram from the top area of the figure. The right-hand side of the tool is dedicated to the time domain response of the system. The process output is shown in the top right area, while the process input is represented in the bottom right region. Depending on the specific interactive tool, different interactive elements may appear in these figures. For tools related to the frequency domain, a similar layout pattern is used. Interactive parameters are again modified from the top left area, and the pole zero diagram is shown in the bottom left region. In this case, the right-hand side displays the frequency domain plots for magnitude and phase. Some specific tools for frequency domain analysis and stability also allow additional graphical representations to be shown on the right-hand side. For example, a combination of Bode, Nyquist, and Nichols plots can be displayed. These representations can be configured by selecting different options from the Options menu. Finally, there is a specific case for tools introducing PID controllers. In this case, the pole zero diagram is replaced by a Nyquist plot to illustrate stability and robustness concepts. We hope this video has been useful and has helped you visualize the potential of the interactive tools that accompany the book. These tools are designed to make abstract control concepts more intuitive, more engaging, and easier to understand through direct interaction. We encourage you to explore the tools on your own, experiment with the different elements, and discover how interactivity can enhance your learning experience. Thank you for watching, and enjoy your journey into automatic control.